Io stands out as one of the most intriguing celestial bodies in our solar system. As the closest of Jupiter's four major moons, Io boasts extraordinary characteristics that distinguish it from any other object we've observed, including active volcanoes, glowing auroras, and a sulfur-rich atmosphere. I'm Alex McCone, and this is Astrum. Join me as we dive into the fiery, fascinating world of Io and explore its wonders. To understand Io, let's first place it within its cosmic neighborhood. Jupiter, the largest planet in our solar system, is orbited by 79 known moons. A few small moons hug the planet's rings, but beyond these lie the four Galilean moons, named after their discoverer, Galileo Galilei, who first spotted them in 1610. From closest to farthest, these are Io, Europa, Ganymede, and Callisto. Further out are Jupiter's irregular moons, which follow more distant, eccentric paths. Io orbits remarkably close to Jupiter, just 350,000 kilometers above its cloud tops. From Io's surface, Jupiter would loom 39 times larger than Earth's moon appears in our sky. Io completes an orbit in a mere 42.5 hours, far quicker than our moon's 27-day journey. Its orbit is synchronized with Europa and Ganymede in a 1-2-4 resonance, meaning Io circles Jupiter twice for every orbit of Europa and 4 times for every orbit of Ganymede. This resonance amplifies the gravitational interactions between the moons, giving Io's orbit a slight eccentricity. This gravitational tug-of-war, combined with Jupiter's immense pull, generates tidal heating within Io, likely fueling its intense geological activity. At certain points in its orbit, Io's surface can bulge up to 100 meters, a dramatic contrast to Earth's tides, which shift ocean levels by about 2 meters. Io experiences tidal forces 300% stronger than those on Earth, driven by its proximity to Jupiter and the influence of the other Galilean moons, ensuring constant geological upheaval. Io is tidally locked, meaning one side always faces Jupiter, just as one side of our moon always atmosphere. However, Jupiter's intense radiation, 10,000 times stronger than Earth's, disrupted Pioneer 10's imaging attempts. The Voyager missions in 1979 revealed Io's true nature. Voyager 1, passing just 20,000 kilometers away, captured vivid images of a colorful landscape with no impact craters, towering mountains, vast volcanic pits, and lava flows. Most strikingly, it detected plumes rising from the surface, confirming Io's active volcanism, the first such observation beyond Earth, excluding cryovolcanoes. Voyager 1 also revealed a surface coated in sulfur frosts, responsible for Io's vibrant yellows, reds, and whites. Voyager 2, observing from 1,000,000 kilometers away, confirmed the persistence of these volcanic plumes over months. The Ulejit Galileo spacecraft, arriving in 1995, provided even sharper images despite mechanical issues. It confirmed that Io's volcanoes erupt sulfur and magnesium-rich silicate magma, similar to Earth's, but with unique properties. The surface features yellow sulfur plains, white sulfur dioxide frosts, and redder polar regions damaged by radiation. Massive volcanic plumes, like those from the Pele volcano, can reach 300 kilometers high and 1,200 kilometers wide, leaving vivid deposits. Unlike Earth's volcanoes, Io's lava often forms lakes within high-walled depressions, such as the 200-kilometer-wide Loki, which generates 25% of Io's heat output. Occasionally, the crust on these lakes collapses, causing intense heat bursts, as seen at Tavashtar, where radiant energy overwhelmed cameras during an eruption captured by New Horizons in 2007. Io's interaction with Jupiter's magnetic field is equally remarkable. Orbiting within Jupiter's powerful magnetic field, Io's volcanic particles form a neutral cloud that trails its orbit. This cloud interacts with Jupiter's plasma torus, a ring of ionized particles moving faster than Io's orbit. Collisions between the torus and Io's cloud ionize particles, feeding the torus at a rate of 1 ton per second, expanding Jupiter's magnetosphere. Io's flux tube, a stream of magnetic field lines, connects its atmosphere to Jupiter's polar regions, creating auroral trails. On Io itself, auroras glow in green, sodium, red, oxygen, and blue, sulfur, adding to its otherworldly allure. Neil. Let's shift to a terrestrial spectacle, the Tonga-Hunga Ha'apai eruption. In late December 2024, this underwater volcano in the Pacific unleashed a series of massive eruptions, culminating in a colossal event on January 15, 2025. Observed by GOES West and Himawari 8 satellites, this explosion was possibly the largest ever recorded, dwarfing even nuclear blasts. The ash cloud, spanning an area the size of Europe, blanketed nearby islands, turning vibrant landscapes into gray, moon-like terrains. Over 200,000 lightning flashes illuminated the plume, a phenomenon still under study, but likely caused by charged particles and ash interactions. The eruption's shockwave, traveling faster than sound, was detected globally, circling Earth at least 4 times. It shattered windows and was audible as far as New Zealand, Australia, and Alaska. Though underwater volcanoes rarely triggered tsunamis, this event's scale caused a modest one, impacting Pacific coastlines. The ash contaminated water supplies and blocked sunlight, threatening plants, though it may enrich soil long-term. Stratospheric ash, containing sulfuric acid and other chemicals, could linger for years, potentially cooling Earth slightly by reflecting sunlight, but also posing risks of acid rain. The island itself, formed in 2014 at a tectonic plate boundary, was split back into 2 by the eruption. NASA continues to study it to understand. Concentrated under the South Pole. This ocean fuels cryovolcanism, with jets ejecting 250 kilograms of water per second at over 2,000 kilometers an hour, forming Saturn's diffuse blue E-ring. Cassini's analysis of these plumes detected water, amino acids, carbon dioxide, nitrogen, and methane, hinting at conditions suitable for life. Enceladus's southern hemisphere, marked by tiger-stripe fractures, lacks craters, indicating a young, constantly renewed surface. The North Pole, older and cratered, lacks plumes. Cassini's close-up images revealed a glacier-like terrain with folded, fractured ice. Future missions to probe Enceladus's ocean could uncover signs of life, but for now, we await new explorations. Phafi. Windshield. We turn to Triton, Neptune's largest and most enigmatic moon. Visited only once by Voyager 2 in 1989, Triton is unique as a captured dwarf planet, likely from the Kuiper Belt, sharing a composition with Pluto. Its retrograde, inclined orbit sets it apart from other large moons. Triton's nitrogen ice surface, mixed with water and carbon dioxide ices, is remarkably smooth, with few craters due to active cryovolcanism. Liquid water erupts from its mantle, freezing into lava plains and calderas. Dark plumes, possibly driven by a greenhouse effect within the ice, spread deposits up to 150 kilometers. Triton's thin atmosphere supports clouds and winds, with seasonal changes thickening it as nitrogen ice sublimates. Organic compounds like tholins, formed by UV light, hint at the potential for subsurface oceans to harbor life-supporting conditions. Triton's dynamic geology and captured origin make it a captivating subject for future study. This our journey through Io, Tonga-Hunga, Enceladus, and Triton. Thanks for joining me on Astrum. A huge shout out to our Patreon supporters. Your support fuels this channel. If you haven't joined, check the pinned comment to become part of our 1,000 Patreon member goal. Enjoy ad-free videos and get your name in the credits. For more cosmic adventures, click the playlist link. See you next time.